Welcome to the Computer Science Professional Development video series. This is series number 2 on the essential concepts in the computer science standards, and this fourth video is on the algorithms and programming overarching concept. My name is Dan Schneider. I'm a high school computer science teacher here in Arizona, and I'm a member of the Arizona chapter of the Computer Science Teachers Association. So first, an overview. The Arizona Computer Science Standards are organized into 5 overarching concepts that span all grade levels. Today, we'll be focusing only on the algorithms and programming concept. When reading the standards themselves, they are organized first by grade level, then by concept, then subconcept, and lastly, an identifying number. In today's video, we'll only be looking at the algorithms and programming standards, which have an AP in the second position. Our goals today are to understand the algorithms and programming concept at a broad level and see how its 5 subconcepts, algorithms, variables, control, modularity, and program development, help guide a progression of knowledge from elementary through high school. We'll look at examples in the K5, 6-8, and 9-12 grade bands with a focus on how this concept progresses through the grade bands. We'll also look at some resources and ways that teachers may already be emphasizing these concepts in their classrooms. So first, a broad overview. What do we mean by algorithms and programming? And first, let's start by talking about algorithms. This definition appears in the glossary of the Arizona Computer Science Standards, and it says an algorithm is a step-by-step process to complete a task, a list of steps to finish a task, a set of instructions that can be performed with or without a computer. In early grade levels, our students experience algorithms when they are learning skills that need to be followed in a certain precise sequence, such as tying our shoes or the steps we need to get ready to leave the house in the morning. You may even use algorithms embedded into classroom routines, such as structured series of steps for taking out supplies or putting them away. Our students also use algorithms outside of the classroom in creative and meaningful ways, such as following a recipe while cooking or completing an art project with a prescribed series of steps, such as color by numbers. Algorithms are also useful for solving problems, such as giving directions to a friend or describing a series of steps that a robot could take to solve a maze. As our algorithms get more sophisticated, they may start to include more nuanced decisions. For example, when getting dressed in the morning, deciding to wear a jacket if it is raining outside. And lastly, algorithms also appear embedded in other subjects, especially math and science. Following a sequence of steps to complete a lab experiment or following a sequence of steps to solve a math problem are both examples of algorithms. Particularly in younger grades, students may be using algorithms along with manipulatives or drawings to solve problems. For example, following a series of steps using place value blocks to represent regrouping when performing addition and subtraction problems. Importantly, none of these examples involve a computer. Instead, the focus is on problem solving and being aware of the steps and instructions you might use to solve a particular problem. When we start to get computers involved, we enter the realm of programming. This definition also appears in the glossary of the Arizona Computer Science Standards. A program is a set of instructions that the computer executes in order to achieve a particular objective. An algorithm that has been coded into something that can be run by a machine. Generally speaking, programming is the act of translating an algorithm into a language that a computer can understand and interpret to solve problems for us. We'll look at a variety of programming environments and languages that could be used throughout grade levels, but there are many more than just the ones in this slide and on this presentation. In lower grade levels, it can be appropriate to use a block-based language. For example, this example from Code.org's CS Fundamentals curriculum. This is both block-based and targeted towards pre-readers. Students can give instructions using pictures rather than language-based commands. These types of environments usually have both unplugged and plugged components, allowing you to start with a tactile, hands-on activity before transitioning to the complementary computer-based programming version. Another popular programming environment, especially at the elementary and middle school level, is Scratch, developed by MIT. Research has shown that starting students with a block-based language improves students' comprehension and persistence in programming when introduced via this block-based language. Scratch also presents opportunities to use coding for their own creative endeavors, designing digital scenes or presentations that can be used as projects in other classes, or creating their own games or using code to design their own personal art projects. Eventually, students may want to transition to a text-based language. One example is web programming using JavaScript or P5.js, which is shown here creating an interactive art design. Web-based languages can be appealing because of the immediate feedback students get from their designs and the ease with which students can share their work widely amongst their community. As students progress through the grades, they also learn more sophisticated commands to incorporate in their programs. We see here examples of functions, loops, and randomness, all to create this design. As students become more fluent with learning a new programming language, it is important to not lose sight of the purpose of a program to solve a particular problem. This can be a problem of personal interest or personal creativity, but also many of the problems students see in math or science classes can be encoded as a computer program, such as the one seen here to calculate the midpoint using Python. It can be helpful to connect programming to other subjects and disciplines, challenging students to use computers to help make these other subjects more efficient and easier to solve for them. A summary of the algorithms programming concept is provided in the state standards and also provided here. It's broken down into 5 additional subconcepts. 3 of those subconcepts are listed here: algorithms, variables, and control, while the other 2 are on the next slide. I won't take the time to read these out loud, but feel free to pause this video and read through these summaries in order to see how these subconcepts are first introduced and progress through the grade levels. Here are the other 2 subconcepts for algorithms and programming. We have modularity and program development. Again, these descriptions are in the state standards, and I won't read them here, but I again invite you to pause this video and read through them to see how these are first introduced and developed throughout the grade levels. Awesome. So let's start by looking at some standards in the beginning grade levels. I've selected several standards from kindergarten and grade 1. A theme throughout the early grades is identifying places where students experience step-by-step instructions to complete a task. We see this in the top first grade standard, which explicitly connects the concept of an algorithm to classroom routines, which you are probably already implementing in your classes. We also see the problem-solving strategy of breaking down a problem into smaller parts, which is a strategy that helps students in just about all of their early endeavors. Another key point is that many standards at this level include the phrase "with teacher guidance," acknowledging that students still need assistance navigating the step-by-step nature of algorithms, especially when troubleshooting algorithms and finding mistakes. This process is generally called debugging, a term which was created by computer scientist Grace Hopper when she discovered an error in her program was caused by a literal bug that had crawled into the computer mainframe of the 1940s and created a short circuit in the machine. It's rare for these literal computer bugs to happen nowadays, but we can still help students debug problems by presenting them with steps that are out of order, then helping them rearrange them into the correct order. 2 great resources at the early elementary levels are from CS in SF and Boot Up. CS in SF is a collection of resources and curricula from San Francisco's efforts to implement computer science throughout all grade levels, including kindergarten and early elementary. They have several curricula available, especially at the early elementary levels. Similarly, Boot Up has a collection of K-3 lessons and activities that show how you can introduce algorithms and programmers to pre-readers using Scratch Junior. Both resources are Creative Commons licensed and can be accessed by teachers for free. In upper elementary, we begin to see more concrete programming concepts and skills. We see variables being used in 3rd grade as a way to remember data, and we see the introduction of events, loops, and conditionals in 4th grade. Importantly, a close reading of these standards shows that these activities can be done either plugged, meaning using a computer and a programming language, or unplugged, with manipulatives and paper materials usually integrated into a larger unit. At this level, students are being introduced to some of the key concepts of developing programs, defining actions using an event, making decisions based on conditions, or repeating actions with loops. But all of this is in service of solving other problems they may have or as part of a larger performance-based project. In addition to tried and true methods of demonstrating understanding, such as writing a paper or giving a speech or creating a presentation, students can be challenged to create a program or create an animation to demonstrate the same understanding in these other subject areas. A great resource at this level has been put together by the Gilbert Public Schools and includes activities for each standard broken down by grade level, as well as advice for how to tweak activities you're probably already doing so they now meet these standards. At the middle school level, many of the standards become more concrete in the skills students need to know for programming and computational thinking. However, there are standards that can continue to be integrated into other subjects or connected to other disciplines. I've highlighted some of those standards here, which teachers can still implement outside of dedicated computer science time. For example, integrated into math or science or ELA lessons. A common theme in these set of standards is the focus on planning strategies to solve problems, collaborating and planning with others on projects, and incorporating feedback from others to revise and refine solutions that meet the needs of a particular audience. In the absence of a standalone computer science class, all of these are standards that can be incorporated in other disciplines. For example, planning out the solution to a problem can be integrated in math lessons when given problems that emphasize the modeling standards. And incorporating feedback to meet the needs of users can be incorporated into ELA lessons as part of peer reviewing assignments and offering feedback to be incorporated into drafts. Essentially, if you have an activity that involves collaboration, feedback and revision, or devising a plan before solving a problem, then there is probably a way to align it to that activity to these computer science standards as well. However, the standards at the middle school level do become more advanced and concrete with the skills that students need to be computational thinkers and creators rather than consumers of technology. At this level, several programming concepts are continued to be developed. In seventh grade, we dive deeper into how variables can hold different types of data and look at complex control structures, including compound conditionals and nested loops. In eighth grade, we see procedures that have parameters being used intentionally to organize code. This attention to specific programming strategies and vocabulary almost necessitates dedicated time for computer science, either as a standalone class or embedded in several units in an existing STEM class. If all of this terminology and description seems overwhelming, that's okay. There are a variety of curricula and professional development opportunities out there that you can use to implement these standards. Many of these newer curricula are designed for teachers without a background in computer science. Many times they include professional development that help build computer science content knowledge in addition to providing sound pedagogical resources. There are many different curricular choices out there, and it's not the goal of this video to recommend a particular one. Instead, there are two organizations that have vetted and consolidated different curricula that are available to teachers and districts. Code.org has their own middle and high school curricula, but they also maintain a large list of curricula available to teachers outside of their own. Similarly, the Computer Science Teachers Association, or CSTA, maintains a list of curricula that also provide professional development for teachers. You may want to reach out to other teachers in your district or neighboring districts, or teachers in your local CSTA chapter to hear a curricula they're using and their experiences with how well it maps to the Arizona standards. At the high school level, we see a focus on students using programming concepts strategically and with intent to make their code more efficient. For example, realizing when lists are an extension of using a multitude of variables to represent a collection of data, and therefore are more efficient than using several variables. Or how functions and objects can be used to represent complex structures in a program. Additionally, we see a focus on program development, using specific collaboration strategies when working in teams to solve a problem, and developing a program with a purpose to serve a community need or to satisfy a personal endeavor. These standards are written to emphasize programming as a foundational set of knowledge open to all students that can help solve problems in other disciplines or serve personal creativity. This is opposed to standards that might present programming solely as a tool for employment and limited only to those interested in pursuing a career in software development. That is not how these are written. One interesting quality to note is that many of the staples of computer science courses, loops or if statements or events or variables, are hardly mentioned at the high school standard because they are instead introduced in earlier grade levels. This is one way that the expectation in these standards may contrast with other high school standards, such as CTE or EdTech, and some resources that could be labeled as high school ready. It's important to appropriately vet these resources and make sure they reach the level of depth and rigor outlined in these high school standards, rather than plateauing at content that actually better belongs in middle school based on the computer science standards. At the high school level, it is probably best to find a curriculum that suits your strengths and the needs of your students and the capabilities of the district. The same curricular resources on the last slide can also be used to find curriculum at the high school level, but there are several other resources that can help with teaching programming to a diverse set of learners. The CS for All NYC organization has created a website of curricular and pedagogy resources called Blueprint, which includes videos of classrooms implementing sound computer science pedagogy. The College Board has also collected a variety of pedagogy and curricular resources as they've implemented their AP Computer Science Principles course, which is an introductory course to computer science and includes a list of approved curricular providers. There are also two websites that focus on computer science pedagogy, CS Teaching Tips and Engage CS EDU, which provide strategies and resources for introducing programming concepts in hands-on, engaging, and inclusive manners to make students of all ability levels feel comfortable learning programming for the first time. They also include strategies to help avoid unintended bias that can sometimes push away underrepresented groups from getting involved with computer science in the first place. So we made it. Thanks for going on this journey with me, talking about algorithms and programming. As a reminder, here were our goals for today. Hopefully you can leave this video with a greater understanding of the algorithms and programming concept and see some ways you can start implementing these standards in your classroom or begin investigating different curricula and resources that can be used to supplement your courses. In addition to the individual resources listed earlier, there are several general resources that may be useful in diving deeper into teaching computer science. We're grateful for the work of other organizations here in Arizona and around the nation for curating and sharing these teacher-vetted resources and strategies. The Arizona Department of Education is maintaining a list of resources, including the ones from Gilbert Public Schools that were mentioned earlier. The Computer Science Teachers Association Arizona chapter maintains a list of news and updates and professional development opportunities here in Arizona. These other two resources were mentioned earlier as great places to find curricula and pedagogy resources for all levels. And lastly, if you're looking for strategies to implement computer science without computers, CS Unplugged is a tried and true resource for implementing computer science away from computers. So with all that, happy teaching. Thanks for watching.